Welcome back. Today we will cover the momentum theorem. Momentum theorem follows from the second law of Newton that the rate of change of momentum of a body in motion is equal to the net external force applied on it. So if capital P is the momentum of a body, then dP by dt, the rate of change of momentum following the particle, is equal to the net external force applied. In fluids, we use control volume. And for the control volume, the material rate of change of momentum P would be given by the local rate of change of momentum del P by del T plus the net efflux of momentum. In the efflux terms, we have written rho V dot A. Rho V dot A is the mass flux at the outlet into V is mass flux into velocity is the momentum. Since the area vector A of a surface is pointing outwards, V dot A positive would imply that this is an outflux. V dot A negative would imply that velocity is opposed to the area and area is taken positive outwards. So V dot A negative means it is a influx. So if we consider the signs of V dot A, then both the terms outflux and influx written in this manner would be with the positive signs. And so we can write F, the net external force applied, would be equal to the rate of accumulation of the momentum within the control volume plus the net efflux of momentum from all the ports to the control volume. This is valid only in inertial frames of reference because the Newton's second law of motion is applicable only in the inertial frames. What are inertial frames? Frames that are either stationary or are moving with constant velocities. That is, frames that are not accelerating. A rotating frame would definitely be accelerating. Now, this is a vector equation and this should be applicable component wise also. So we can write this for the x component, the y component and the z component. Now, for steady flow, the rate of accumulation of momentum P would be 0 and so the net external force applied would be the sum of rho V dot A times V at all ports, the net efflux of momentum. A very simple equation. We need to worry about the sign convention for the efflux term, and as was said before, at the inlet the sign of the mass flux is negative in this picture that we have shown because the area vector is outwards and that is towards the left and down, and the velocity vector is towards the right and up. So velocity vectors is positive in the x and y components, whereas the area vector is downwards. So the sign of the mass flux is negative and sign of the velocity component positive. The sign of the momentum efflux would be negative. If, however, the port was like this, is again an inlet port, here the sign of mass flux V dot A is negative, but the velocity component is also negative. So the sign of momentum efflux is positive. At an outlet like this, the mass flux is positive, the velocity component is positive, so that the momentum efflux is also positive. But if the exit is like this, the sign of the mass flux is positive. area vector is towards the left, velocity vector is toward the left, and so the mass flux is positive and the velocity component is negative, so that the momentum flux has a negative sign. We'll follow this convention in writing all the momentum fluxes. Now let us consider the external forces. The first we talk of surface forces. The intensity of surface forces is usually expressed in terms of stresses. Stress is defined as the force per unit area. If you have a body in a fluid, the pressure in a fluid is a normal stress. At the nose of this body, there is pressure acting inwards. This is a normal stress. The tangential component is termed as the shear stress. There are no tangential stresses in a stationary fluid. But this may not be true if the fluid is in motion. And both the normal and tangential components of stress may be present in such a fluid. So, the total external body forces would be expressed as the integral over the whole surface of minus P dA. dA is pointed outwards, P is towards the surface, towards the body, so it is minus P dA, plus tau, the shear stress, times dA. Next we consider the body forces. Body forces, on the other hand, act throughout the bulk of the control volume. These forces, such as those due to gravity or electromagnetism, act from a distance, and their intensity is expressed as per unit mass. The only body force which will concern us in this presentation is that because of gravity, the intensity of which is minus gk. K is the unit vector in the vertical direction. The gravity is vertically downwards. So, the intensity of the gravity forces, that is weight per unit mass, is minus gk, where g is the acceleration due to gravity. So, the total body force is obtained by integrating over the volume the mass of the body, rho times dv times the acceleration due to gravity, which is minus gk. So, this expression gives you the total body force. Now, we have to choose the control volume. The choice of the control volume is dictated by the following suggestions. A, we should choose a control volume such that as few external surface forces act on the control surface constituted by the control volume. Obvious, the lesser the forces, the fewer terms we will need to incorporate within the equation. The fluid velocities at the entrance and exits are normal to the control surface there, so that the mass flow rate rho v dot A at the ports are evaluated simply as rho VA, not the vector but the scalar rho VA. Otherwise, v dot A, we'll have to worry about the angle between the area and the velocity. The third recommendation is that the control surface should, as far as possible, not be chosen with fluid adjacent to it. Otherwise, the presence of the shear forces on such surfaces may introduce insurmountable problems. When analyzing the flow systems that are moving or deforming, we may choose the control volume which is moving or deforming, but make sure that their flux is calculated using the velocity relative to the control surface. Let's do a few examples. This example here is of a fireman's nozzle. In a flexible hose, the water is coming At the nozzle inlet, the pressure is 300 kilopascal gauge. The nozzle reduces the flow diameter from 50 millimeter to 25 millimeter as shown. There would be force in the nozzle because of this pressure and because of the efflux of water. So we'll have to hold this nozzle rather firmly. We'll need to apply a force to hold it. Let the external force applied be Fx in the x direction. Now we'll write the momentum equation for this, and we will use the x component of momentum equation because we are interested in evaluating the force Fx in the x direction. This is the control volume that we take. We draw all the external forces on this. There are only two. The pressure P1, the gauge pressure P1, and the force Fx. There is atmospheric pressure all around, but atmospheric pressure all around leads to zero force. A uniform pressure all around a volume leads to zero net force. So the equation in the x direction would be Fx. The total external force would be the total net efflux of x momentum, because this is steady flow. So there is no rate of accumulation. The total external force is P1 gauge time A1, the area at 1, and Fx, both positive. The flux of momentum at the inlet is minus rho Va at 1 times velocity at 1. This is negative because mass flux is negative and velocity is positive. So the product is negative. The other efflux is at the outlet. The efflux of momentum at the outlet is rho Va2 times V2. And this is positive since the mass is coming out, so it's positive, and the velocity is in the positive direction. So the equation of momentum reads P1 gauge times A1 plus Fx is equal to rho Va at 2 V2 minus rho Va at 1 V1. This is simplified to obtain this result. We can apply Bernoulli equation between point 1 and 2. And if we apply Bernoulli equation between point 1 and 2, V1 square by 2g plus P1g by rho g should be equal to V2 square by 2g, since Z1 is Z2 and P2g is 0. Using the value of P1g, which was given as 300 kilopascal, given the value of rho for water, and given the area ratio 1:4, diameter at 1 is twice the diameter at 2, so V1 is 1/4 of V2. Using this information, we get the velocity at the exit to be 25.3 meters per second. Once we know V2, we can calculate V1 and plug it in the equation on top, and we get a result that the force is minus 353.8 Newton. Why minus sign? Minus sign means that this force would be in the direction opposite to the direction that we assumed this force to be in. We assumed this to be positive, pointing towards the right. The force would be to the left. So a fireman would have to apply a force to the left. That is, the nozzle by itself would tend to go towards the right. So a fireman would have to apply this rather large force, 353.8 Newton is a fairly large force. Let's do another example. A simple example of a force on a vane. Let there be a vane at 60 degrees, a jet of water coming from an orifice of diameter 2 centimeters at 10 meters per second impinges on this vane and is divided in two equal streams, one going up the vane, the other going down the vane. We have to determine what would be the force that would be needed to keep this vane in place. Let that force have two components, Fx and Fy, as shown. Now to determine Fx, we need to write the x component of the momentum equation, and to determine Fy, we need to write the y component of the momentum equation. What control volume do we choose? We could choose a control volume like this, where the control surface runs next to the vane. This is not a very good choice, since shear force would act on this control surface all along the vane, and so too would the pressure force be. It's not easy to determine those forces. So we may choose a control volume like this. In this case, there is atmospheric pressure all around, like there was in the first case as well. The jet of water is out of the nozzle, so it will have a pressure equal to atmospheric at all three locations. And then the solid forces within the support of the vane would become external forces, Fx and Fy, as shown. This is a fairly good control volume, but we can improve upon this a little bit by considering the area of this control volume as normal to places where there is water influx and water efflux. So just a minor changes here and here to make the control surface normal to the velocity at this end. So we'll work with this control volume. We'll first work with the x momentum. X momentum flux at the inlet is minus rho VA at the inlet, minus sign because it is the influx of mass into V, the velocity there. At the outlet marked 1, rho VA at 1, positive since it's in a flux of mass, into V cosine 60 degrees. There is an x component of velocity which is positive. So if V is the velocity, then the x component V cosine 60 degrees. The angle of the vane is 60 degrees. So both the mass flux as well as the velocity components are positive. And so this flux is positive. At the outlet mark 2, rho VA, the mass flux is positive, it's coming out. But the x component of velocity is negative, minus V cosine 60 degrees. The mass flux is positive, but x component of velocity is negative, so that the momentum efflux here is negative. So the x momentum equation, the net external force, the only external force on this control volume is Fx, horizontal. Force is Fx. So Fx is the net efflux of momentum. You see the efflux at 1 and efflux at 2 cancel one another out if the jet divides equally. So the mass flux at 1 and 2 are the same. The velocities are equal but opposite. So their flux at 1 cancels out their flux at 2. So there is only a net influx or a negative flux of rho, which is 1000 kilogram per meter cube into velocity square, velocity is 10 meters per second, into the area. Area is 2 centimeter, so it's pi by 4 into 0.02 meter whole square, and there is a minus 31.4 Newton. So the force that we need to apply to hold this in place would be in the negative direction of 31.4 Newton. We have to hold the vane back. It will tend to move in the direction of the jet, so we'll have to hold it back. Let's do the y momentum equation again. At the inlet, the y momentum is 0 because there is no component of y velocity there. At the outlet marked 1, the mass flux is rho VA, positive, and the y component of velocity is v sine 60 degrees in the positive y direction. Both the mass flux as well as the y velocity components are positive, hence this efflux is positive. At the outlet mark 2, the mass flux is rho VA at 2, positive, and the velocity in the y direction is negative, minus v sine 60 degrees. And so the efflux at 2 is negative. And as we can see clearly, the two effluxes have equal magnitude but opposite sign, so they cancel out. So the net efflux across the whole of the control surface is 0. And so the net external force Fy is 0. There would be no force in the vertical direction due to this jet of water playing on this vane. Let's do another example, this time with a moving control volume. Let there be a curved vane on which the water enters horizontally tangent to it and leaves at an angle of 60 degrees after turning upwards. And let this wave be moving with a velocity of 10 meters per second to the right. To analyze this, let's take a control volume as shown. This control volume where the external force is Fx and Fy as shown. The influx of momentum at 1, and there is a flux of momentum at point 2. As mentioned before, since the control volume is moving, but it is moving at a constant speed, so the frame is inertial if we attach the frame to this control volume. So we attach the frame to this control volume, and then the velocities we have to measure with respect to this control surface. So now the inlet velocity at location 1 would be 30 meters per second minus 10 meters per second, or the relative velocity of 20 meters per second. Within this frame, we apply the Bernoulli equation. The pressure at point 1 and point 2 are the same, and if we can neglect the difference in the elevation, the velocity at 1 and 2 in this moving frame would be same, that is 20 meters per second. The mass flow rate, the mass flux, is m dot is equal to rho VA is equal to 14.1 kilogram per second. This is negative at 1 and positive at 2. In flux at 1, a flux at point 2. So the force Fx is equal to m dot into V2 cosine 60 degrees minus V1, and this is equal to 14.1 kilogram per second into 20 meters per second into cosine 60 degrees minus 20 meters per second, which is the value of V1, and this gives you a net value minus 141 Newton to the left. This is the force we need to apply to hold the vane moving at a speed of 10 meters per second. That is, to prevent any acceleration of this vane. So that means effectively the water jet is applying a force towards the right. And to overcome this, we have to apply a negative force, minus 141 Newton. Similarly, the force in the y direction, Fy, is equal to the net efflux of y momentum, and y momentum comes out only at 2. So this is m dot V2 sine 60 degrees, and that come out to be 121.7 Newton. That is, we have to apply a force upwards. So the force because of water jet on the vane is downwards.